we can use valence bond theory to describe the bonding in complex ions. Hopefully you remember a little of this from Chem 1A. So if we have two ligands, the geometry will be linear. We'll have sp hybridization, and those two hybrid orbitals will be across from each other. If there are four, it will be tetrahedral with an sp3 hybridization. There's the tetrahedron. Square planar. They're showing it as dsp2 because if this was like 4s and 4p, that would be 3d. I'm not sure why they switched from the earlier chapter where they would have called it what's wrong with that?
Which one?
DSP2.
The ordering of the...
Well, besides that.
Oh.
Oh, no, never mind. Never mind. It's fine. I was thinking ligands around the S, and there's only three. The S is one of the things. So that's a funny one that we didn't see in 1A. Because if you use the sp3, you're going to get a tetrahedron because of the arrangement of those orbitals. If you use a d orbital instead of one of the p orbitals, then you'll get this. And then this is the same as in Chem 1A, except we called it sp3d2. So a coordinate covalent bond is where you have an overlap between a full atomic orbital and an empty one, right? So one person is being very generous. I'm sharing both of my electrons with you. In the complex ion, the empty orbital will be on the metal ion. That's why the ligands have to be Lewis bases with lone pairs that they can donate, right? So the hybridization of those orbitals corresponds to the geometry of the complex ion. So these would be empty orbitals, and those orbitals are there even if nothing is in them, just like a hotel room still exists even if no one is sleeping in it, right? So valence bond theory gets the geometry, that's awesome. But there's some other things that we observe, color and magnetism, that valence bond theory doesn't explain. So we've got attractions between the electrons on the ligands and the positive charge on the metal ion. But then those ligand electrons are also going to repel metal ions in the unhybridized d orbitals. And so when we have the octahedral ligands, they're going to overlap with two d orbitals, and that's going to increase their energies more than the 3d orbitals that fall between the ligands. So here we have, we've got our 6 ligands, and this is showing the different d orbitals that are present. D orbitals are just a little funkier than the p orbitals. So here we have this ligand and that ligand lining up directly with this orbital. They're going to interfere with each other. So you're going to get strong repulsion, and that's going to be higher energy. Here, you're going to get 4 of these overlapping with the 4 lobes of another d orbital. And again, that's going to be higher in energy because they don't like being near each other. For these ones, the ligands are falling between the lobes. So there's more space, less repulsion. And here, this one and that one, they're falling between right? Can you see that? Here, this ligand looks like it's going to stick onto that orbital. But that orbital has electrons in it. It doesn't want more electrons, and there's going to be repulsion. Here, the repulsion is less because these guys are between. This guy's, much better because he's like further away from these. But these have weaker repulsions, and so we get this orbital splitting. So on the free atom, the 5d orbitals are degenerate, all the same energy. When it bonds with the ligands, we get this splitting where 2 of the orbitals are going to be higher in energy and 3 are going to be not lower in energy than this one, but lower than the others. And this difference in energy is important. Any questions? Yeah, so electrons will go into the lower energy orbitals first. Yeah. Depends on how many electrons there are, right? But the rules we learned for filling would be that you put 1 in here and 1 in here and 1 in here, and then pair them up before you go up here. And we'll see that whether that happens or not depends on how big this difference is. Any other questions? So that difference in energy is called the crystal field splitting energy. The magnitude, how big it is, depends on the ligand. So there are strong field complexes that have a big amount of splitting, large crystal field splitting energy, and there are weak field complexes where the splitting is smaller. And this explains the beautiful colors that we observe from many complex ion solutions. So hopefully we remember that color is due to the absorption of light energy by the electrons. And so if we have something that's black, it's going to absorb all wavelengths and not reflect much of anything. Something that's white does not absorb, but will transmit or reflect all wavelengths. And then the colors that we see in between are due to it absorbing some visible light, but transmitting other light. So this would be transmitting red, and this would be transmitting blue. And if this is transmitting blue, the solution is probably absorbing the complementary color. So anybody who took art classes, here's our color wheel. This is not, the complementary color business is not something people made up. It's science. So what we see with this guy, Hexa Aqua Titanium 3, it's purple. If we look at its absorbance, it's going to absorb strongly in this region. So the greens and yellows is going to absorb, and it's going to transmit or reflect in the lower places. This is done with spectroscopy. The wavelength absorbed when an electron makes a transition from a lower energy to a higher energy. So here, light of these wavelengths has the correct energy to move from the lower level of the split d orbitals to the higher, moves an electron up. It's absorbing that wavelength of light. when we subtract those colors from all of these colors, what we see is this. And so it's not just that, oh, well, this thing is transmitting purple and absorbing everything else. It's absorbing some of these things and not others. And doesn't even necessarily have to be one big hump in the middle. So the crystal field splitting energy can be calculated by looking at the wavelength of light that is absorbed. So the energy of a photon of light is equal to Planck's constant times the frequency, which is the same as Planck's constant times the speed of light divided by the wavelength. So these are the wavelengths of the transitions between the different colors. And so we can actually calculate that. So this complex ion is yellow. Estimate the crystal field splitting energy in kilojoules per mole for this ion. So we're going to go back and look at this color wheel. So if it is appearing yellow, then what is it absorbing? It's probably absorbing strongly in the purple. Now we're not going to get a single answer. This is going to be an approximate answer. But it said all we had was yellow, so we'll go with the middle of yellow and we'll go with the middle of the purple. So that would be what, 415 nanometers of wavelength? And then we can calculate the energy per photon. So the wavelength being absorbed was 415 nanometers, and the energy of one photon is equal to hc over lambda. Can somebody look up Planck's constant? I think it's
6.63 times 10 to the
good. And is that joule seconds?
That's a great question. I have the numbers sorted here.
Speed of light, 3.00 times 10 to the 8th meters per second. Yeah, it's joule seconds. And then down here, we're going to put our wavelength. We need to pay attention to units. Joule seconds, the seconds are going to cancel here. We want to keep the joule because that's a unit of energy, and so we want to get rid of the meter. This is kind of an example of how you could fudge your way through stuff, just making the units work out. Here you have to kind of choose the right constant, but still doable. So I'm going to write 415 nanometers, 415 times 10 to the minus 9 meters. .63 times 10 to the minus 34 times 3 to the 8th divided by 415 to the negative 9. I'll give it 3 sig figs. That's probably very generous, but. So that's the energy for one photon. We're asked to give the energy in kilojoules per mole. So we could say that this is joules per photon. So we're going to take that 4.79 times 10 to the minus 19 joules per photon. And I'm going to say there's 6.022 times 10 to the 23rd photons per mole. So the photons got fixed. And then I need to convert kilojoules. I want kilojoules, and I get rid of joules. Kilo means 10 to the 3. So 1 times 10 to the 3 kilojoules is 1 kilojoule is 1 times 10 to the 3 joules. And some of you still occasionally have issues with, oh gosh, Minnesota on my calculator. This is the new one. It's the 5 button. Just avoid that. $288 kilojoules per mole. It's very unfortunate. Any questions? So some ligands are typically strong field and others are typically weak field. And so this is called the spectrochemical series. It lists them in order of their ability to split the orbitals. So cyanide tends to give the largest crystal field splitting energy, and then nitrite, and then what does En stand for? Ethylene diamine. So ethylene diamine, ammonia, water, hydroxide, fluoride, chloride, bromide, and iodide. So iodide is typically a weak field splitter. So they'll be splitting, but they'll be very close in energy. The metal ion also has an effect. If you have higher charge, it pulls the ligands in closer and magnifies the effect. So you'll get a larger delta. So, any questions about that? Magnetic properties. So I kind of mentioned this. Hund's rule, the electrons occupy degenerate orbitals singly first, and then they pair up. Just like if you were to, be staying in a hotel room that had 5 beds, and there were 4 of you, and you didn't, it's not, you're there like for business, and these are strangers, right? It's a weird situation. You're each going to take your own bed, right? You're not going to sleep with a stranger unless you have to, right? Actually, for that one, the bus analogy works a little better. It's not as weird. We'll just do the bus analogy. You get on the bus, and are you going to choose a seat? They're always double seats. I don't know why. Are you going to sit next to a stranger, or are you going to take your own empty seat? You'll take your own empty seat. Once all the empty seats are gone, well, got to sit down with a stranger. The stranger's okay with that because those are the social rules, right? You do get to sit down. Okay? So, when the orbitals are half filled, the next electron has a choice. It can pair with an electron in those lower energies, or it can go into an empty orbital of higher energy. And what makes the difference there is what's the difference in energy. So this would be hexacyano iron 2. Yeah. Is known to be diamagnetic, Remember, diamagnetic, all the electrons are paired. Because di means two, and it's like the animals on Noah's Ark, they went in 2 by 2. So diamagnetic. Paramagnetic, pair sounds like a pair, but it's not that word. Para is the other, there's unpaired. So here we have the strong field ligand causes a large difference in energy between these d orbitals. So, you go 1, 2, 3, the fourth electron comes in, and he'd rather sit with a stranger than, pay extra to go up there. And so this one will have all of its electrons paired. But if you have hexa-aqua iron 2, water is a weak field ligand, and so the difference in energy between these is small. Now, they didn't do a very good job of drawing that one big and this one small. They kind of look the same to me. Probably reused the font or something, I don't know. But this is smaller. So now, 1, 2, 3, 4, 5. These guys are going to go up there to have their own orbital, and then when we have to start pairing up, they'll start filling up these lower ones again. That gives us 4 unpaired electrons. Without crystal field splitting, we would not predict that this one would be diamagnetic, because normally the 6 electrons would go in there, and you'd only have 1 pair up, like this. You'd have 4 unpaired. Any questions? So if we have strong field ligands in a complex, there will be fewer unpaired electrons. Those are called low spin complexes. If we have weak field ligands, there will be the same number of unpaired electrons as on the free metal ion, because they're going to go ahead and use all the d orbitals, just like the metal ion did without its ligands. Those are called high spin complexes. And it's only metal ions with 4 or more d electrons that can have this splitting possibility.
The high spin, low spin, is that a reference to the spin numbers of the electrons?
I don't think so. I think probably what it is when you when electrons are in the same orbital, they spin pair, right? So
Right, it's like you have a
less
spin number,
less
one
spinning, right? And so then the unpaired are going to be more spinning. Yeah, more unpaired electrons, more spinning. Because when they pair up, it's not that they cancel each other out, but they can coexist.
Yeah,
And so then they're
the
not
spin
going to
numbers can-
they're not going to interact with other things. Yeah. PChem. How many unpaired electrons are there in the complex ion hexachloro iron 3? So we need to know how many electrons there are in that iron 3 ion, right? We need to know if chlorine is a high field or low field, strong field or weak field. And again, aren't you glad you don't have to memorize this? So we go back here and look and see that chlorine is typically a weak field ligand. So the splitting's going to be small. So we'll have 3 that are low and 3 that are high, but this delta is small. Now, to get the electrons, it's probably best to look at the electron configuration for iron. Where'd you go? So it's argon. And then 4s2 3d6. Did I do that right? It's harder to count when you have to jump. Yep. That's an iron atom. Here we have an iron ion, right? These are chloride ions. They have a -1 charge. Overall, this is -3 charge, so it must be Fe3+, right? So we're going to remove electrons. Which ones do we remove first? The 4s. So, bye-bye. I thought I was going to scribble that out, but the eraser worked too. And then the next one's going to have to come from the D. So I only have 5 in there. So I have 5 electrons to put into this. I guess you could call it an orbital diagram of sorts. So 1 electron, 2 electron, 3 electrons. Where's the 4th electron going to go? It's going to go up because it's just a little bit of difference. Okay, so this is turning into a train analogy. So there's the regular car, and then there's the special car, you know, that costs more money, like first class. So regular and first class. And so here you're going in, and all of the regular seats have somebody in them. But there's open seats in first class. The difference in price between coach and first class is only a little bit, so you're going to go over there. But for the other ones where it's a lot of money to go over there, you're going to suck it up and sit with a stranger. Okay? That's a new one, just tonight. 1, 2, 3, 4, 5. How many unpaired electrons? 5. How many unpaired electrons in hexes, cyano, cobalt? 2? 2. Well, is cyanide a strong field or weak field? Strong field. You can kind of guess that because they probably wouldn't give you 2 weak field problems on the same thing. So, strong field. So there's a lot of splitting. The difference in energy here is large. So let's look at the electron configuration for cobalt. Again, it's argon, and it's just got 1 more electron than iron. Positive 2 charge, lose 2 electrons. We're going to lose the 4s electrons. So that leaves us with 7 electrons. So we put these in here. 1, 2, 3. Are they going to go up to first class? No. 4, 5, 6. Now number 7 has no choice. This coach cab is full, and so he has to pay and go to first class. So how many unpaired electrons? 1. You don't get these answers right if you don't use crystal field splitting. There is splitting for other geometries, tetrahedral and square planar, but it happens differently. The tetrahedral splitting is the opposite of the octahedral, where you have 3 that are high energy and 2 that are lower in energy. This is usually going to be high spin. There's going to be a lot of unpaired electrons, so delta is smaller. Again, so glad nobody has to memorize this. And then we have square planar splitting, which is even more complicated. And we get 4 different levels. We got 2 down here, and then 3 different ones, right? This one is nearly always low spin, meaning they're going to be paired. And you can see how that could happen because you're really not going to get past here until you have 6, most likely. So, any questions?